Hi. What if I told you that one of the most powerful AI models is not using GPU? Google, the company behind Search, YouTube, and Gemini, decided that GPUs are not enough for their AI future. So instead of buying more GPUs from NVIDIA, they built their own version of their chip. It is called TPU, Tensor Processing Unit. And today, I will explain why Google used TPU over the GPUs, not with market trends, but with real engineering examples or real engineering reasons. By end of this video, you will understand when GPUs make sense, when TPUs win, and what this teaches us as AI engineers. So let's start with a simple truth. GPUs are amazing. They power gaming, rendering, robotics, research labs, and most AI training today. But here's the catch. GPUs were not designed for AI. They were designed for graphics, drawing millions of pixels in parallel. AI just borrowed the GPUs because they happen to be good at parallel math. Google looked at this and asked one dangerous question. What if we remove everything that is not required for AI and build a chip only for neural networks? That question gave birth to TPUs. To understand TPUs, you must understand one operation, matrix multiplication. Almost everything in AI, including convolution, max pooling, attention, embeddings, reduces into simple matrix multiplication. GPU can do matrix multiplication parallelly, but TPUs are really good at it. Inside TPU is something called a systolic array. Think of it like an something that is like intended to do matrix multiplication only. The data flows rhythmically, multiply, accumulate, move forward with almost zero wasted motion. But GPU, on other hand, do do good well in the matrix multiplication, but they carry tools that they always do not need. So Google didn't want the flexibility, they wanted maximum throughput for one specific job, matrix multiplication. Now comes the real killer reason, power efficiency. Imagine running AI models not once, not for research, but 24/7 for billions of users. Every Google search, every translate request, every YouTube recommendation, that's continuous inference. At Google scale, even a 10% efficiency improvement means millions of dollars saved per year. TPU deliver much higher performance per watt than GPUs for tensor workloads. Less power, less heat, more compute. GPUs burn energy to stay flexible. TPUs burn energy only to do AI math. This is why Google could never rely on GPUs alone. Google usually thinks or plans strategically, and Google does not think in single machines. Google thinks in fleets, tens of thousands of accelerators running in parallel. Buying GPU means vendor lock-ins, supply shortages, paying premium margins. But by building TPUs, Google controls the pricing, controls the roadmap, design hardware around their workloads. TPUs are not cheaper per chip, they are cheaper per training run and per deployed model. At Google scale, that difference is enormous. So this is where Google really wins. TPUs are not just hardware, they are part of an ecosystem. TensorFlow, JAX, XLA compiler. Google controls the model, the compiler, the runtime, the hardware. XLA rearranges the model graph specifically to match the TPU execution. This level of optimization is almost impossible on general GPUs. GPUs must support graphics, CUDA kernels, many programming styles. TPU only care about how fast can I run this neural network. That's it. And here is the real lesson. Google didn't build TPU because GPUs were weak. They built TPUs because general purpose tools hit a limit. As engineers, this teaches us something powerful. First, specialization beats flexibility in the scale. Second, hardware and software must evolve together. Third, the best system is the one optimized for your exact needs. GPUs are incredible, TPUs are ruthless. Google needed ruthless efficiency. So the next time when somebody asks you why didn't Google just use GPUs, you will know the answer. Because at Google, at scale, efficiency beats flexibility and specialization beats generalization. If you enjoyed this deep dive into AI systems, I will be breaking down more real world engineering decisions like uh, this, not the theory part, not the hype, just how things actually work. I will see you in the next one. Bye.